All right, so in this lesson, we're going to take a look at the actual forces that we are going to be applying for most of Unit 2. Now, we're going to go through and I'm going to introduce this first slide that we've got. I do recommend that you keep this in a spot that you can find in your notes. We're going to start off with the force list. So one of the things that I recommend for my students is this, especially if you're new to physics. If you haven't had a lot of practice with it, one, you may not know what things are and are not forces. We're going to give you a list of common forces that show up in introductory physics problems. In fact, with the exception of one that isn't going to be necessarily on this list, or I may have it there at the end because it's one that I introduce for my students later. For the completeness of this video, I may go ahead and include it so that people watching this can get that down. But if you are one of my students watching this, at least as of the filming of this video, the last one, spring force, is one that we'll take a look at towards the end of this semester in a couple of months or so. But for the AP grading or the AP pacing guides, it is a force that would be included in this. The list that we're about to do is not a comprehensive list, but it's a very good list and will cover most of the forces that you're going to encounter in an introductory Physics 1 class. Okay, going through the list. And as I was saying, if you're new to physics, not only are you not necessarily familiar with the forces themselves, but one of the hardest things that I've seen for new students to adapt to is the idea of when they're doing a free body diagram, to apply Newton's second law, we want a free body diagram to see all the forces acting on an object, because all the forces together actually generate the changes in motion, cause the acceleration is a way of looking at it. So we need to have a free body diagram with all the forces acting on an object. For new students, one of the hardest things for them to actually come to the conclusion of is, I'm working on my free body diagram, how do I know that I'm done looking for forces, especially if you're new to this? This slide, the force list, is going to be key to that. So we're about to write this out. I'm going to summarize it, and then through the lessons that we do as we move forward, you're going to see how I recommend applying. Okay, so that's the context on it. I'm also going to put the forces in order based on how common they are, at least for the majority of them. The most common force that we're going to take a look at and have in our problems is going to be the force of gravity. The next most common is going to be a normal force or several normal forces. In this case, this may be your first time actually seeing that phrase. So a normal force is a physical contact force. So this is anything like touching or hitting or pushing or anything like that. Normal forces are the technical term for that. We're also going to have forces of friction. These are all very common forces in introductory physics classes and on the AP exam. Okay, so we're going to have friction, that's next on here. Tension. Some instructors like to combine tension and normal forces, but when we go through in that lesson, I'll tell you why I keep tension separate, but it is very similar to normal force, but it has a few exceptions. The next one that we're going to introduce is called drag. Now that's the technical term, drag force, but in broad applications, you all can imagine it as air resistance. Now, for algebra-based physics, we may talk about this conceptually, so it's one that we will talk about, but when we go through our actual lessons, I will also give you the equation related to it. For calculus-based physics, this is one of the places where we will actually apply integral calculus to look at and predict the motion of an object that is subject to air resistance. So for calc-based physics, this is going to be a big focus for us to add in later. And then finally, well, not finally, because I'm going to add the other one in on this list, but I apologize, my board is doing a thing where it kind of deletes part of it. The next one that I like to make reference to is thrust. This is rocket or jet engines. Rockets or jets. Now, on the AP exam, they've actually asked quite a few questions where you have a little fan that's attached to, say, a cart or something like that. The fans will also approximate as a force of thrust. To my knowledge, the AP exam doesn't necessarily ask you about the force of thrust, but my background is, among other things, in aerospace engineering, so this was actually a very important force for us to talk about, and it does carry over in quite a few applications onto the AP physics exams, so I like to include it in my list. Now, for my students in the class right now, when we were doing this lesson, here is where I would end the list, but for this, I'm also going to add in a spring or elastic force. I'm going to call it spring force, but I'm also going to put that this is often called an elastic force, and I'll mark a couple of notations on that. but this is the force from a spring. We'll go ahead and include this in the list for people who are not necessarily in my class, because I want this to also be something more broadly applicable. So, force of gravity. We follow the same convention, at least as of the filming of this video, that the AP exam follows. All forces will be kept track of with a capital F, and I do recommend doing that. There are some places, some university classes and other places, where they might put the force of gravity, as we're going to see later in this lesson. It is known as weight. They may represent it with a capital W. That is not used on the modern AP exam for any of the resources that I have seen, and I don't like using it. For me and my students, anytime we're dealing with a force, we represent it with a capital F and a lowercase subscript, or not necessarily lowercase, but a subscript, I mean, that represents what type of force. So force of gravity is F little g. For a normal force, we represent this as capital F, capital N for our subscript. For force of friction, there are a couple of different notations on this, but I'm going to try and use the modern one for the AP exam, and it's a pretty good one as well, F sub F for the force of friction. We're going to see that that can get a little bit more complex because there are actually a couple of types of friction. But in general, F sub F is a blanket approach to friction. Tension, F sub capital T. Now, one of the things that I'll bring up on this is one where even in some of my videos, I go to kind of the old way of representing this and do a force of tension as capital T. I don't necessarily recommend that, but sometimes if you have a lot of ropes and wires, oh yeah, let me fill that in, I apologize. Tension happens when you have things like ropes or strings, so that you've got an idea of what we're looking for on that. But if you've got several strings, sometimes you have to do like FT1, and then when you split it into components, it becomes a pain. So that's one that I kind of break with my rules and sometimes do as a capital T, but broadly we will refer to it as F sub T for emphasizing the force. For drag force, F sub D, and I believe that's usually how it's represented on the AP exam, though a lot of times they'll just say it's a force F. For thrust, in this case, since FT was already taken, I do F sub TH. And I'm going to give you two of them for the spring force. Well, actually, technically three of them for my students. I'm going to list that first because this video is more for my students than any of the others. I like to use F sub SP. There are a couple reasons for that. The AP exam, however, uses F sub S, and another common one is F sub E for the elastic force. I've seen all of those used. For my videos and my students, we will preferentially use F sub SP because we will sometimes refer to static friction as F sub S when we do a breakdown of the types of friction. So these are common ways to represent the spring force. Now, once again, for my students, we will cover this in a later lesson, but for an introduction broadly to Unit 2 for AP Physics, all of these would be standard forces that would show up in this section. Okay. Now, here's the thing. As we go through, even in the lesson today, I'm going to show you how we use this list to know that we are done making our free body diagram. But I want to start with this. Keep track of where this is in your notes, especially if you are new at physics. This list is going to be very, very useful for you. Okay. Now we're going to start with the other part of this lesson, going into what the next series of lessons are going to be, which is going into a deeper explanation of what that list means. And that means we're going to start off with the force of gravity. Force of gravity. I'm also going to point out that this is commonly called the gravitational force. That is also a completely appropriate way of identifying this. I'm going to put a little note on here. We're going to be learning about the force of gravity, and this is a very useful and commonly applied approach to it, but this is actually the force of gravity near Earth's surface, or technically any planetary surface, or I should say any sufficiently large object that it is like a planet. So this could apply to our moon, as we're going to see in some of our lesson and in future lessons that we work with. But we're looking at the force of gravity from a large nearby object. In this case, it's simplest just to say, hey, we're looking for the force of gravity on an object on Earth, on the surface of the Earth. Okay. First off, a description of what the force of gravity is. It's a force of attraction always attraction, never repulsion, at least from our current understanding of physics, but it's a force of attraction between massive, and I'm going to put a little star next to that, massive objects. We're going to take a deeper dive into gravity in later lessons towards the end of this unit, where we see what Newton actually introduced as the full understanding of gravity. It's a bit more complex than what we'll look at here, and what we're going to introduce here will actually work for most problems that you're dealing with, as long as you're not actually working with the space program, basically. So, as long as you're on Earth, which most of us are, this one is going to work very well. Okay, let's talk about this word massive. So I'm going to ask you a few questions. I want you to think what the answers are, or say them aloud if you would like. I'm going to mention an object, and I want you to identify if it is massive or if it is not massive. Okay. The planet Earth. A mountain. Me, Sanchez. And finally, a proton. Tiny little thing. Okay. For a lot of my students, they will say massive when we say Earth, and probably when there's a mountain. And if they're feeling particularly cruel, when I ask if I am massive, they will say very clearly, Sanchez. Maybe I had too big of a dinner last night. But that being said, a lot of times they'll be like, he's in charge of my grade. Let's be nice to him. You're not massive, Sanchez. And then when I get to the proton, they'll go, no, that's not massive. All of those things are massive. And that's something that we need to set up right here, right now. On my exam or the AP exam, whenever you see a word, if it has a common application, so the common way of describing massive implies that you're talking about a big, heavy object. So the Earth, the mountain, not necessarily me, and definitely not a proton. That's the common application of the word massive. But scientifically, massive simply means object with mass. And what that means is, yes, a planet is massive, but so is Sanchez, and so are you. And I almost wrote photon, the one thing that doesn't belong on this list. I need a proton, which is actually very tiny. Even an electron, which is even tinier than that, and has a mass of, or at least a rest mass of 9.11 times 10 to the negative 31 kilograms, even that has a mass and therefore is a massive object. An electron will also engage in gravitational interactions. For our purposes, the only thing that you might encounter, and it's not really talked about in the first semester or first year of college or university physics, is going to be photons. So that comes in AP Physics 2, usually, or some of the chemistry classes. There may be other things, but at least for the regular interactions, just about any object is actually going to be massive. I want to bring that up because especially if you get into the later parts and say AP Physics 2, that sort of thing, they will use the word massive to give you a heads up that the object does have mass and therefore will engage in gravitational interactions. Okay. Now that we've introduced what the force actually is, it's an attractive force between any objects that have mass. Here's our equation. I believe this is the latest version from the AP equation sheet, and it looks like this. We have Fg for our force of gravity. Like all forces, it is a vector, so it will have a direction associated with it. And then we have the absolute value signs, but that's when you're dealing with a number. If you put that around a vector, we're actually talking about the magnitude. The magnitude means ignore positives and negatives, which is regular for an absolute value, but it also means it doesn't matter if it's pointed off at an angle or anything like that. We just want the total number. This is the number that describes how strong the force of gravity is. And that's going to be equal to the mass of the object that you're looking at and the gravitational field strength or the acceleration due to gravity. Okay, so we're going to see this a lot as we go forward, but I've introduced a new equation. I'm now going to tell you what each of the parts are, and we're going to talk about what units they have so that we know how to use this equation. F sub g with the absolute value signs is the magnitude of the gravitational force from usually the Earth for our viewpoint onto the object, whatever object you're looking at. Okay, the mass. This is the mass of the object that you're looking at. And G. We're going to have to spend a little bit of time on G. G is, for my students, and what we normally refer to it as, I'm going to add a word here. It is the local acceleration due to gravity. Now I say local because depending on where you are, that value might actually change. So near the surface of the Earth, we usually use the three significant figures. The standard value is 9.81 meters per second squared. Now, actually at our altitude, because we're not at sea level, and our latitude, among other things, there are a lot of factors that can go into that. Here in this classroom, it's probably closer to 9.80 or maybe even 9.79. So you could use the actual local, that's what I mean by local, whatever it is at your point. But as we're also going to see in this lesson, this equation does allow for you to go through and account for being on other celestial objects. So on the moon, instead of 9.81, we would have, I believe it is 1.67 meters per second squared. If you're on the surface of Mars, for instance, a different planet, the effect of gravity is different there, and the acceleration due to gravity on the surface of Mars is, I believe, 3.63 meters per second squared. In later lessons in this unit, towards the end, we're actually going to show you how you can calculate that and predict those things. But for now, we represent this as calling it the acceleration due to gravity, and it's whatever it is around where you're solving your problem. However, the AP exam and people using the proper terms, I already did, might call this the gravitational field strength. So on the AP exam, they may refer to it that way. I want you to know that this term is basically another way of saying acceleration due to gravity. The way we look at it in my class, the acceleration due to gravity usually makes a little bit more sense, but I can assure you that the gravitational field strength is more technically correct. Now, it's actually going to take about a week to go through the finer points of understanding what a field is, and it's mostly important for when you get set up for AP Physics 2 or AP CE&M or the equivalent college class, because electric and magnetic fields become very important for being able to solve those problems. I find it less important for gravitational applications, so we won't talk about it too much in my preparation, and my students, at least thus far, have not suffered greatly for going light on that on the AP exam. That being said, the technical term is the gravitational field strength. So the AP exam or some of your materials may make reference to that term. That's just another way of referring to the acceleration due to gravity. Whenever you see G, little g, in an equation, it should be positive 9.81 meters per second squared. In this case, G is set up to be the magnitude. Many of my students, and you all may too, be used to putting a negative on this. I'm going to emphasize this. The acceleration in the y in projectile motion was negative 9.81 meters per second squared. And why? Because the acceleration, the actual acceleration, is a vector, and therefore, since gravity pulls things down, we need the negative. In this case, we have g, which is not a vector, it's actually just the magnitude of the acceleration, and that is why it is positive 9.81 meters per second squared. Whenever you see a g, a little g in the equation, do not put the negative. If you do, we're going to see that it's actually going to throw off your calculations, and you'll predict that things fall up instead. The biggest thing that you need right now is, in any of the equations that have little g, it is always a positive, whatever that value is. For Earth, it'd be 9.81. I'll also go ahead and bring up this. For the AP exam, it is common to actually make it 10 meters per second squared to simplify calculations. Okay. Here's where it gets a little bit more interesting. Our forces, as all of our forces are measured preferentially in newtons. The mass of the object is measured in the SI unit for mass, which is kilograms, not grams. And g is the local acceleration due to gravity. Well, that's an acceleration, so we would describe it as being measured in meters per second squared. Here's where things get a little bit tricky, and you may see on the AP exam, I've seen it multiple times. The gravitational field strength is actually measured in Newton per kilogram. Now, When you learn more about fields, you'll see that that's probably a better way of describing what the gravitational field strength is, but it turns out that it's functionally the same, at least for gravity. This is not the case for electromagnetism, but for gravity, the field strength is effectively the acceleration due to gravity on an object. Please remember from one of our previous lessons that a Newton is a kilogram times meter divided by second squared. So if I expand the Newton, the kilograms would cancel out and would leave me with meters per second squared. It's possible that on the AP exam they may give you a value in Newton per kilogram, and that's why I'm emphasizing this, so that you can be ready to work with that. It's another way of writing meter per second squared. And it's only really applied on these when they're describing the acceleration caused by gravitational effects. Okay. So this is our introduction on gravity. I know that my videos have a little bit of problem if they start running long in my recorder, so I'm going to pause there for just a moment, and we'll be back in just a moment to actually see how to apply this. All right, so I started my camera back up, so hopefully we don't have any interruptions. I've had instances where the video cuts out, so you may have seen that already. I just feel compelled to mention why I'm doing that. Okay, we just finished, as you've been watching this, introducing the key concepts for the force of gravity near the surface of the Earth. So now here's where I'm going to show you how to use this equation. So our first and main example is going to be applied to me, Sanchez. In this case, I checked, and my mass, the mass of Sanchez, is approximately 72 kilograms. Now, my students, and for many people watching this video, if you're not from the, say, metric countries, you're probably more used to dealing with pounds. I will tell you this, 72 kilograms, hand-wavy conversion, but doing a comparison, in Europe, they would say, hey, I'm 72 kilograms, and in America, or other places that are using similar units, I'm about 160 pounds, give or take a little bit. Take that as you will. Maybe I did have a big lunch or a big dinner last night. Okay, so on this, I'm going to walk you through how we find the force of gravity applied to me, Sanchez, and then we're going to see how we can use that to make predictions on things. So first things first, I'm going to take my equation. What I'd like to know is this, the force of gravity on Sanchez. So I've got force of gravity, and then I'm going to mark it here with S for the force of gravity being applied to me, which is different than the force of gravity being applied onto this pen, or this paper, or any of the other objects around here, unless, of course, I guess they're 72 kilograms. So in this case, while I could technically write out the force of gravity with the vector sign and the magnitude bars, let's save some time and just call this Fg. But remember, it only gives you the number, and then I'm going to show you how we work with it. So Fg is equal to mg. So for me, Fgs would be equal to ms times g. Well, I don't have a gs because g is just a constant value for the surface of the Earth. So on this, I would have the force of gravity applied to Sanchez is equal to 72 kilograms times either 9.81 meters per second squared, or you could write that as newtons per kilogram. If it's Newton per kilogram, then the kilograms cancel out, leaving us with newtons. Or, if you write it this way, kilogram times meter per second squared will give us newtons. In this case, the force of gravity on Sanchez, when we multiply that out, comes up to, let me double check my notes here, let's see, right at about 706 newtons. Now, on the actual AP exam, we would probably call this 10 instead, and I would end up with 720 newtons. That's perfectly fine, especially for the AP exam. If you're doing my homework, or if you're not told to use 10, then use 9.8, because the computer won't tell you that it's a correct answer if you use 10. Okay, so here's the force of gravity on me. Okay, now I'm going to show you how we can actually apply that. Let's take this into a sample problem. We got a building here, and we're going to say, Sanchez fell off the roof. Sad face. At least sad face for me. Some of you will be taking my test in the near future, and therefore you might actually be smiling at the prospect of me falling off a roof. Oh, it's me. So, purple sweater caught in the wind. I wear a sweater around my waist pretty much all the time, and it's usually purple, because purple's the best. Okay, so here's what we want. I fall off the roof, and I would like to predict my motion. I want to know what my acceleration is going to be. Now, right now, you may be going, well, Sanchez, we've already talked about that. You're an object near the surface of the Earth, so your acceleration would be that of free fall, the acceleration due to gravity. That's great. It's wonderful starting off with a problem that we know the answer to so that we can check our answer. But I'm going to show you how we're going to go about applying Newton's second law. I want to know my acceleration. In my class, we use the following equation. The sum of forces is equal to the mass times the acceleration. On the AP exam, they also have a just as good way of writing it, that the acceleration is equal to our sum of forces divided by our mass. In short, accelerations are caused by all the forces acting on an object. The most common mistake students make when they're new to this is they will take one force and set it equal to the mass times the acceleration. Don't fall into that trap. Sometimes that's an appropriate application, but only if there's one force only acting on the object. Remember, Newton's second law says all of the forces together cause the acceleration. So the only way to predict the acceleration of an object is to look at all the forces acting on them. Okay, here I am in midair, flying off of the building. So I'm already away from the building, and this is me going to fall down and go boom. So here's what we're going to do. I want to apply Newton's second law, so I'm going to do that free body diagram that we talked about. So I'm going to draw a dot. Okay, now we need to find all the forces acting on me, and here's where I really recommend, especially if you're new, don't get super excited and go, oh, I know what force. I want you to go instead back to the force list. This is why I said it's so important. Especially on the simple problems, you're going to say, I don't need that. But later, when I give you a problem that has 8 or 9 forces acting on one object, this is going to be invaluable. So I'm setting you up with the tools you need to solve any problem, no matter how easy or how complex. So here's what we're going to do. We have our force list up. We're going to go down the list. Gravity, normal force, friction, tension, drag, thrust, and spring force are the main ones we need to check for right now. Okay, oops, one too many. Here we go. So let's go down our list. First force, gravity. When I'm flying through the air, is there a force of gravity being applied to me? Yes, there is. Which way is the force of gravity directed? Forces are vectors, so they have a direction. In this case, gravity pulls stuff down, so I'm going to do an arrow downward, and I'm going to mark it F(g). Now please remember, on free body diagrams, you have the dot. Your arrow must start on the dot and move in the point in the direction of the force. Make certain there is not a gap between your arrow and your dot to get full credit in my class and on the AP exam. And it's good practice in general. Okay, we've got the force of gravity. Usually you only have one of those, but maybe not. We'll see later in the unit. Okay, next up, normal force. Now, here's why, because we haven't gone through all the other forces, I gave you some info on that. I said that a normal force is any type of physical contact force. Well, when I'm out in the air over there, is there anything touching me? I'm not touching the ground, I'm not really touching any walls. There's nothing touching me other than, say, maybe my clothes, but I actually counted my clothes in the 72 kilograms. I went and stood on a scale and did a little bit of math. I actually have a scale that does give me a value in kilograms, but neither here nor there. So in this case, I have no normal forces because nothing is touching me. And we're going to look at the normal force in our next lesson. Okay, going down the list. Friction. Friction is a force from two surfaces rubbing together. Well, that would require me to be physically in contact with something, like sliding along a wall or the ground or something. I'm not touching anything, so there aren't any frictional forces. Next up, tension. Are there any ropes or wires connected to me? Well, not in this problem, no. Maybe in a future problem, I'll be bungee jumping or something like that. But on this one, I've got no ropes or wires, so no tension. Drag. Now here's the one that gets a little bit tricky, because in real life, if I go jumping off the building, there will be some air resistance being applied to me. But for an introductory physics class and on the AP exam, you are instructed to ignore air resistance unless you're specifically instructed to include it. We're going to keep with that, and we're going to say we're going to ignore air resistance on this one, so we're going to skip over drag. Thrust. Do I have any jet engines or rocket engines attached to me? Well, no, so I'm not going to draw that in. But if you're busy laughing and going, well, when will that be the case? Wait till you get to my sample problem about a rocket-powered fridge. All right, and then the last one for us in full preparation, though I wouldn't necessarily have this in my regular class, is spring force. Do I have any springs attached to me? Well, no. We've now reached the bottom of the force list. So we know that we are done. This is our complete free body diagram. I can't stress this enough. My experience has been new students, one of their first problems that they run into is they never know when they are done with a free body diagram. That's what the list will help you do. Get used to using it, and when you get to the bottom of the list, you're done and you have all of the forces, no matter how complex the problem is. Okay, now that I've got this, I see that we have a simple situation where I have only one force being applied to it. So adding up all the forces is going to be super easy. So I've got sum of forces equals my mass times my acceleration. In this case, my sum of forces, the only force that I have is Fg. But here's where I'm pulling from my free body diagram. So if I had other forces, I would add those into it. But one other thing, forces are vectors. My force of gravity is down, so I'm going to put a negative here. This is why we don't put the negative in the other spot that I mentioned. We use the positive because we're going to keep track of the down direction here. Okay, I'm going to set that equal to the mass of Sanchez times the acceleration of Sanchez, because this is the net force acting on me. Well, we found out just a minute ago that the the magnitude of the force of gravity on me is 706 newtons, and that will be equal to my mass, 72 kilograms, times my acceleration at this point. I can divide both sides by 72, and we will end up with negative 9.81 meters per second squared equals the acceleration due to Sanchez. Now, that agrees with what we could have predicted immediately, but I will bring this up. In a future problem, maybe I have a parachute, at which point I might have an upward drag force or something like that. We could talk about it in a couple of different setups, but I could say that the parachute serves to slow me down some or keep me from going at the full acceleration due to gravity. We're going to see some samples of that in the next lesson. But here is the basics of how you apply Newton's second law, particularly onto an object subject to only gravity. In this case, you'll notice that we used my mass, 72 kilograms, to find 706 in the first place, and then we used 706 and then ended up getting this back. So another way of writing this, so that you can see it, might look like this. Well, we said that in this case, negative Fg is equal to ma, and since Fg is nothing more than the mass of the object times the acceleration due to gravity, and I set that equal to the mass of the object times the acceleration, I can divide both sides by m, and we get the following. And no matter what the mass of the object is, our acceleration near the surface of the Earth will be negative g. That's why all things fall with the same gravitational acceleration, at least near the surface of the Earth, and ignoring air resistance or, technically, any other forces. Okay. So now that we've got that, we've got one last thing that we need to take a look at. Well, actually, let's take a look at two last things. One, different locations. Okay, so here's what we're going to do. Sanchez on Earth, Sanchez on the Moon, and Sanchez on Mars. Now, the equation I said originally was it applies near the surface of the Earth, but more broadly, we could probably describe it as near a planet. Anywhere that the acceleration due to gravity is kind of a constant number, and we'll study that more later in this unit, towards the end. But in this case, I would say that g on the Earth is equal to 9.81 meters per second squared. G on the Moon is equal to, I believe it's about 1.67 meters per second squared. It's about 1/6, 1/7 the effect of gravity on Earth. And then finally on Mars, we've got 3.63, I believe, meters per second squared, or Newton per kilogram. So on this, doing a quick calculation, the force of gravity on Sanchez on Earth, I was about to calculate it up, but we already know that. I already ran that number. It's 706 newtons. This is directly equatable to about 160 pounds. Because pounds is a unit of force, and newtons are as well. In fact, that's the last part that we're going to talk about. Fg on the Moon. So I'll do Fgm. In this case, I would take my mass, 72 kilograms, times 1.67, or whatever the appropriate value is, and we would find that this comes up to about 120 newtons. this is about 1/6 of the force, the weight, that I would be on the surface of the Earth, because the effect of gravity is actually much less there. So this comes up to, let's see, I could do the ratio on this, but I remember this being just a little under 30 pounds or so. So that's 30 lbs, not 301. It's about 30 pounds. I would be much lighter on the moon, but, and I want to emphasize this, I would still be 72 kilograms. We're going to talk about that at the very end of this. But first, I'm going to show you how to find the force of gravity on each of these things. So we would then take 72 kilograms times 3.63, and the force of gravity on me from the planet Mars would be about 261, howdy, and that would be about, let's say it's about a third of that, so we'd be somewhere in the ballpark of about 60 pounds. So I would weigh less on various celestial bodies because of the effect of gravity. Which brings us to the last thing that I'm going to actually have as part of this lesson. Okay, first thing to note is this. The important takeaway. Another scientific definition. Remember how I said earlier that there are words that people use day to day, but they don't always use them correctly. And there's a scientific definition. The word weight is used a lot day to day. Weight scientifically describes the force, oh, let me write that in red, I guess. The force of gravity on an object, in this case from, say, the Earth. But specifically, the weight is the force of gravity. So in this case, it is appropriate to say the force of gravity on Sanchez would be, at least near the surface of the Earth, that would be 706 newtons. And therefore, Sanchez's weight is 706 newtons. It is not appropriate to say that my weight is 72 kilograms. This is a no-no. The metric countries are doing it wrong. So here's the thing, I kept using 72 kilograms. That's the difference between mass and weight. Mass is the amount of material I'm made of. So it is true that if you take me and put me on the moon, I would be much lighter and I could jump much higher. It would be easier to pick me up because gravity is less there. But it doesn't mean that I have any less material. Your mass is actually a measurement of inertia, among other things, but it also is based off of how much material you have. It's a nice simple way of keeping track of it. So on the moon, it would be easy to lift me up, at least compared to the Earth, but that doesn't mean that I don't weigh anything or that I don't have any, or my mass is decreased. So for instance, to push me would still require the same amount of effort, the same amount of force. You can't just go up to the moon and go, and then I go flying off into space because I'm so lightweight. You do a at me, I'm gonna nudge a little bit at most because my mass is still 72 kilograms. The only way for me to change that is to cut off an arm or something. My weight, however, which is the force of gravity, is a combination of my mass, how much material I'm made of, and the effect of gravity in that area. So this is a key thing to understand. It is also something that I referenced a little bit ago. The unit pound, which is used in the American system among others, but the unit pound is actually a measurement of force, so it is 100% correct to say that I have a weight of 160 pounds on Earth, and that I have a weight of about 30 pounds on the moon. That is an appropriate statement. It is not appropriate to say that I have a weight of 72 kilograms on Earth, because I also still have a mass, which is the appropriate term, of 72 kilograms on the moon. Mass is something different than weight. Weight is based off of the force of gravity. The metric countries are using it wrong. The last thing that I'm really emphasizing with this is not only the terminology, but on my materials in the AP exam, you may see the following statement. A box of weight, 200 newtons. This is a correct statement. Weights are measured in newtons because they are a force of gravity. What they're saying is the force of gravity on the box is equal to 200 newtons, which means 200 newtons is equal to the mass of the box times the local acceleration due to gravity. If this were 10 meters per second squared, then we would have the mass of the box is 20 kilograms. So when you read this, a box of weight 200 newtons, don't think that it's 200 kilograms. It is not. And it's not a typo. This is the correct statement. In this case, the acceleration due to gravity is not actually 10, it's a little bit less. So the mass of the box would be a little bit more than 20 kilograms. But for my class and the AP exam, that's a fair enough approximation for a lot of the problems that we do. Okay, the last thing in this lesson is understanding that weight scientifically means the force of gravity on an object. All right?